Good morning, everybody. So today there will be a small, like there is something going on over here. So I will have to just briefly attend for the door sometime. But hopefully, yeah, it shouldn't be too much of an interruption. Let's see. Okay. So let me just get started. So yeah, let's begin today's class. So yesterday we had begun the area of statistics, and the first thing that we discussed yesterday. So am I audible? Is the connection quality clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, thank you. So let's begin. So yesterday what we were discussing was a field called probabilistic inequalities. We saw two things. We saw what was called as Markov inequality. And then what we saw next was Chebyshev. So in Markov inequality, we have a non-negative random variable. The premise is non-negative random variable. And in Chebyshev, there is no such restriction. So what we were interested in the tail probability. So probability that x, if that is x is the non-negative random variable x. Okay, what we had is probability that x is greater than or equal to a, okay, is less than or equal to e power x by a. So that's what we saw in the Markov. Then what we did, we derived another inequality, the Chebyshev inequality. Here, instead of this is the one-sided tail, here we will have two-sided tail. Okay, so the two-sided tail says probability that x minus mu, okay, so this is greater than a. Let me use epsilon because that's what we will be using whenever we talk about this error. So this is like the error, right? So x is, so excuse me. So I will have to answer this call. Just a minute. About that. So what I was saying is not this. Yeah. So yeah, what we were discussing was the error, right? So this is like a error. So let me try to. Yeah, you will not see this is like a error now, but when you see in the context of weak law of large number, it will become very clear that this is somewhat like an error. So let's ignore the fact that I said something error here. But any case, this inequality, what we get is this is related to variance of x divided by epsilon square. Okay, so this was Markov inequality. This was Chebyshev inequality. What we did with then is that we then talked about a estimator. So estimator of mean, right? What do I mean by that? So let me choose some interesting color. So let's use this side of the screen. So we have estimator of mean, right? So basically what we said, suppose X is a random variable, okay, with unknown mean, mu. It is unknown to you because you have not understood how the population distribution is, but it is fixed, right? It is a fixed number. You just that you don't know it. Okay. And then what we did was we withdrew several samples, X1, X2, X3, all of this. We took samples from which are actually all of them are X, and they are independent and identically distributed random variables, right? And then we came up with the estimator MN. Okay, the idea of the estimator was we are planning to say what is the mean. We are trying to derive what is the mean. Okay, so for n, mn, the n here, what we are saying is we are adding n of them. Okay, this is what we did yesterday. And then we saw something, right? So first, yeah, what did we say? So since mn is an addition of random, each of this is random numbers, right? When you add random numbers, you'll also get a random number. So it has an expectation, it has a variance. So the expectation of this mn was mu. This we saw, that is good, right? So this expectation being mu is good. This is called as a unbiased estimator. Okay, so it is it is, you are going to get to mu. Okay, for every mn it is mu, so it's unbiased. It's not like having some other component. Then what we also saw was the variance of mn, and this we showed it to be sigma squared by n. All right. Now, given these all properties, we came up with the weak law of large numbers. So this led us to weak law of large numbers. Okay, so what we said here, so we have an estimator mn, okay, and we are looking at basically the errors. What is the probability of the estimator making an error? So this is the mu, which is fixed but unknown to you. So what is the chance that you are away from some epsilon? Okay, so we said that, let me just make some space. Okay, let's so what we said is limit for every epsilon greater than 0, whatever error level that you choose. Okay, so think of this as error level. Okay, and what we said is as n tends to infinity, probability that you make an error, which is represented by this, right, mn minus mu, is greater than epsilon. Okay, this probability goes to 0. This is what we said. And this convergence, if this happens, we say that mn converges in probability to mu. All right. So let me just begin from here. Let's talk about a few things around this. We will also refer to some of the things that Sitsikis discusses, so that we cover, all the things that are necessary as part of this, because you can then go back and read the textbook. But yeah. So are there any questions up until this point? Ramnath, is everything okay?
Yes, sir. Fine.
Okay. So now let's move on. So this thing, so what we essentially said is mn goes to mu in probability, but the idea, so these are called modes of convergence. Okay, so let me just say this. So what we saw, one mode, what we saw is called convergence in probability. Okay. So basically it is this convergence that you saw here. We say mn converges in probability to mu. In today's class, as part of the next topic, we will also see what is meant by convergence in distribution. Okay, so this you will see. Okay, and it has some interesting applications. Okay, so we will see this. But before we get there, the way we proved this was by using Chebyshev, right? So what we did was we said probability that mn minus mu is greater than equal to epsilon is less than or equal to variance of mn by epsilon square. Okay, this left hand side is actually equal to sigma square by n epsilon square. Okay, so that's how we proved this. So this, let it be there in the back of your mind. Okay, so this is the way we proved this. Okay, so now there is yeah. So this mode of this modes of convergence probability is a tricky concept. So let me try to give the example which Sitsiklis gives. Okay, so there is an example in Sitsiklis video. So what is the example is he's talking about random variables yn. Okay, so how does yn look? So it's a discrete random variable. Okay, and the PMF is this. Let me just clear that a little bit. The PMF is it takes two points support. So it's 0, it is having some probability, and at n there is some probability. At n, the probability that it takes the value n, this is 1 over n, and 0 has the rest of it. So this is this takes the probability 1 minus 1 over n. So is the distribution, so each yn, now you know each yn how it looks, right? So for example, y1, okay, will have, y1 will have, how will it look? At 0, at 1, okay, it will have 1 over n, which is 1. So the entire mass will lie at 1. Okay, let's draw one more. Y2, what it will have? At 2, it will have a mass of half. Okay, the remainder mass will be at 0, which is also half. Okay, let me draw y3 once again just to get the idea. Okay, so y3 will have a little bit more mass. So it will have 2/3 at 0, and at 3 it will have 1/3, and so on. Okay, now if you ask, okay, now the question is, does yn converge in probability to a number? That is the question. Does it converge in probability to a number? Suppose if you ask this question, you can make the observation that as n increases, right, more and more mass is falling on 0, right? The random variable is taking more and more weight and putting it in 0. Okay, so it is a logical candidate for us to consider. Okay, so let us consider basically probability that yn minus 0. I'm saying yn. So the question that I'm asking is, does yn converge in probability to 0? Somebody has a question? Let me see. Okay. All right, I heard some noise, so I thought someone is having a question. Anyway, so basically what I'm asking is, given yn, does it converge in probability to a number? Okay, so let us consider, let's try to answer this. Okay, so let's choose an epsilon for our convenience, and let's look at this probability for every epsilon. So let us fix, okay, epsilon to be let's say 0.01. Okay, so that is if you know, that is 1 over 100. Okay, so now let's see. So what is p y1 minus 0 greater than 1 over 100? Yes, so this is actually going to be the entire mass will be 0. So there is y1 is here, right? Okay, so at 0, I'm looking at an interval 1 over 100. Okay. Yes. So I'm looking at this. So what's the probability that this happens? I don't know if people are following, but let me just say. So this is going to be, the error here is going to be 1 because no mass, y1's entire mass is here. Okay, so it is not, 0 is not approximating this well. So this is 1. Okay, so let's try to do once more. What is the probability that y1, y2 minus 0 is greater than 1 over 100? Okay, so y2, if you see, so, and I will draw this. So basically I'm interested in what is the mass that is lying outside this. So that is here. Okay, this is going to be half. All right. So basically what is happening is this error that I'm making is going to keep on reducing. Okay, the only point that lies outside this interval is 1 over n. So in general, probability that yn minus 0 is greater than epsilon, okay, with epsilon the choice being 1 over 100, this is equal to 1 over n. Okay, and we can see that if you limit n tending to infinity, p of yn minus 0, okay, greater than epsilon. Of course, for first I have fixed the epsilon here. This is going to 0. Is this clear? I don't know if this became confusing, but let me repeat. Okay, so the idea is I have to fix an epsilon and I have to see with respect to epsilon, are the errors going to 0? Okay, so that is what is the question. Okay, so then if you see this carefully for y1, okay, the mass that lies, that is not at 0 is completely at here. Okay, this happens with probability 1. For y2, the chance that y2 and 0 there is a disagreement is when y2 is at 2. Okay, this is happening with probability half. So same idea keeps happening. You keep discussing, you keep seeing this. 1 over n is the probability that lies outside of 0. Okay, so that is why this probability is going to 0 for any error. So if you choose any error, you will see that you can do this. All right. Okay, so I believe this discussion was clear. Okay, so let me just ask this because since this might be confusing. So are there any questions? So if this is clear, please let me know. I still see there is some confusion, I think. If you have any question, please feel free to ask, okay? Okay, good. So coming back, what we have shown now is that yn converges in probability to 0, okay? So similarly, let's draw the parallel. What we saw in the other case was mn converges in probability to mu, right? You remember this was the weak law of large numbers. Okay, and what was expected mn? This was also mu. So basically what we got that mn converges to, in probability, so you have to put a p just to indicate this, to expected value of mn. This happened. Okay, but in this example, you will see that this is not the case. Even though yn converges in probability to 0, it is not the case that expected value of yn is not equal to 0. You will see that. Okay, and there is some interesting things about this. So let's do that. So expected value of yn, what is this? So this takes two values, right? 0, it takes with probability 1 minus 1 over n. Okay, and then it takes a probability with 1 over n, it takes the value n. That is what is yn. So what is this expected value of yn? This will be 1. Similarly, let's try to do variance of yn. Okay, so variance of yn is expected value of x square minus expected value of, sorry, expected value of yn square minus expected value of yn whole square, right? So So let's do that. So expected value of yn square is 0, again 0 square with probability 1 minus 1 over n, plus n square with probability 1 over n minus 1. Okay, so this is going to be n minus 1. So what do we see? What is the conclusion? We see that expected value of yn is always 1. Okay, and variance of yn is n minus 1. Okay, so as n tends to infinity, okay, this will always, it converges, the thing will go to 1, whereas variance of yn, so variance of yn will tend to infinity, whereas expected value of yn, okay, it will remain 1 as n tends to infinity. Okay, so basically what are we saying? So we saw in weak law of large numbers, we saw that mn converges to mu, and it also was the case that expected value of mn for every n was mu. Okay, but in this counter example, what we are seeing is yn is converging in probability to 0. Okay, and it is not the case that expected value of yn is 0. Okay, so basically what you have in weak law is a little bit more stronger than what is usually provided in the convergence in probability. All right. So this is just the, so I personally feel that this discussion makes people confused, but I didn't want to omit it because this is part of the Sitsiklis lectures. So this can be confusing. Okay, so please ask me any questions that you may have here, and I will be happy to again explain the whole thing. Okay, so I believe things are all right. So let us now talk about some applications. So applications. The first one we will talk about is exit polls. Okay, so let's say there is an election. The recent election that happened was American election. Let's not take Indian election because it will get controversial. So let's talk about US elections. So in US elections, there were two candidates, right? So let's call them candidate A and candidate B, right? Now there is a fixed but unknown, right? There is a fixed but unknown support for candidate A, let us say, and that we will call it as mu A. Okay, isn't it? So there is a fixed but unknown support for candidate A, which is mu A. Okay, now we will have an estimator. What is my estimator? I'm going to go and ask n random people, okay, whether they support candidate A or not. So basically what I will do is xi, okay, will be 1 if support candidate A, okay, will be 0 if support candidate B. All right. So my estimation for mu A is what I'm trying to estimate is given by mn. Okay, mn will be x1. So I will ask n people, x1 plus x2 plus xn divided by n. Okay, is the idea clear? So what am I trying to do? I am trying to find out what proportion of the population supports candidate A. Okay, so let's just change colors a little bit. Okay, so that's what we would like to do. Okay, and if you have to be confident, right? So basically what I need to do, so I don't know, okay, so let's say mu A is fixed but unknown. Okay, and I am interested that whatever, so this is a percentage, right? Fixed but unknown percentage. So let's say example of mu A could be 47.3. This could be one example, or it could be 55.2, right? See, what I would be interested, if at all I have to do a poll like this, I should ask basically, with 1% confidence, I should be able to, with 1% accuracy, I should be able to tell. What that means to say, I would like to have some guarantee that my estimate in this case will be between 46.3 and 48.3. Okay, I would like to design the n. My choice is here only, right? I can only increase this or decrease this. This is the choice of pollster, isn't it? So that is what the pollster decides, how many people to actually ask. Suppose if I tell I want to have 1% accuracy, okay, so this is this, or in this case it will be 54.2 to 56.2. Okay, so that is my desired level of accuracy. Okay, so in other words, what I am saying is that I want the probability that I make a error. Okay, my error should be within this accuracy. So that means Mn minus mu A. Okay, I want 1% accuracy. So anything without beyond 1% accuracy. So this is the epsilon or the accuracy. Okay, the accuracy that the error that I make. So this whole thing is error. Okay, I want to design this in such a way that I am having at least 95% confidence. Or in other words, my error probability is 5%. Okay. So what I'm saying is Mn that does not belong to mu A plus mu A minus 0.01, okay, and mu A plus 0.01. This is the error, right? This probability has to be 0.05. Okay, and this is called the confidence. Okay, so I think it's a good time to ask people some questions. So my first question here in this, focus your eyes on this. Okay, tell me which is a random thing here. Which quantity is random? Since I'm talking about probability, right? So which is the thing that is random here? Yes, anybody?
All the xi.
Mu A and Mn.
All the xi's are random and mn is random, whereas this is a fixed integer, fixed number. Okay, so if I can write this as minus 1% if you want in percentage notation, but any case, okay, this is fixed. This is fixed. You may not know it, but this is fixed. So this is random. Okay, that is the first important observation. Okay, so what can happen since mn is random? Sometimes it may not lie in the desired range. Okay, when it doesn't lie in that desired range, that chances has to be low. Okay, so that is called as the error probability. All right. Okay, let me just again quickly do a poll. Can I quickly ask if everything is okay so far? Yes. So what is okay? So somebody has a question. Advay is having a question, so let me answer that. Anybody has any question, please ask me. All right. Advay, it is totally understandable that there is a scope of confusion. So let me just make it clear. Okay, so mu is this is an unknown thing. You don't know. Okay, but see, you are supposed to design. You are going to do exit polls. Okay, and let us say it is a simple system. You are looking at only one constituency. Okay, and there are only two candidates there. So in order to be sure who wins, what you need to know is that you should know what proportion of the population supports that candidate, right? And suppose to do that well enough, I designed to say that my accuracy has to be 1%. Okay, so that means if it was 47.3, I want my estimate to lie with as much chance in this range. Okay, so I want my estimate Mn to lie between this interval. Okay, or if the actual supporting population was 55.2, my exit poll should be designed in such a way that it lies here. So this 1% is my choice. This is the choice of the choice made by pollster. Okay, the pollster is making this choice. All right. So this is something that I choose is an accuracy level. What accuracy are you happy with? So 1%, if you write it in terms of a number, it becomes 0.01. Okay, so that is why we are saying 0.01. So this is that 0.01. Okay, now if I look at, so this is the error, okay, and I want to control the error. I don't want the error to be too large. Okay, that is what is called as 0.05. This is the probability of that error. I want to make the error as small as possible. Okay, but since I can keep on making it small, to be really useful in practice, I choose a level of 5%. Okay, this is standard. You can make it if you want 99% also, but yeah, so this is called the error. 1 minus that is called as the confidence. Okay.
Sir, it is the error in what exactly?
So error in, so okay, what is this quantity Mn minus mu a greater than 0.01? What is this?
That will be the probability that the two-sided tail probability.
Two-sided tail probability with the accuracy that I have chosen.
Yeah.
I am failing that. I am not able to meet that. That is what this says, right? Correct. These two are the same. Do you see that? They are the same.
Yeah.
So I am saying, what is the chance that I make an error beyond the acceptable accuracy level?
Okay.
So that is the error probability. Okay.
Okay.
Is this clear now?
Yes, sir.
Yeah. Okay. Good. So now,
Sir,
yeah.
excuse me, sir. Just one.
Yeah.
one
Please
more
go
thing.
ahead.
That
Yeah.
how are we so sure that the answer, like we are working on decreasing, like we are working on increasing the accuracy, but how do we know the answer? For example, we are doing an exit poll, okay, and we are just managing, okay, let's reduce the error. Let's reduce the error to 1% or to 5% or to 10%, whatever we are choosing. But how do we know that we are choose the mu a to be 47.3%? Like we know the answer first, and now we are just setting कि कितने लोग बैठाएं ताकि हिसाब सही बैठ जाए, like something of that sort.
No, we don't know that it is 47.3. Let me make it very clear. We don't know. So this mu a is not known to us. This is not known. Okay. Siddhant, does that make sense? It's not known. I'm not saying it is known. I just gave you two examples. Suppose if it was this is what the error level will be. Suppose it was this is what the error level will be. Okay.
Okay, sir.
All right. I don't know. I'm not going to use mu a in any of my calculations, as you will see. I will not use it.
So we are just like mu is the right answer. If like mu is the right answer, the probability, like, and we can calculate how many people we have to ask the questions like the poll without knowing what the actual answer is.
Yes, so that you get within 1% accuracy. So once you do this, and let us say the number turns out to be 48%, I can say that within plus or minus 1%, the actual number lies.
Okay, sir.
Yeah. So, but this is random. So this depends. This can change. All right.
But then, okay, sir. Yeah. Thank you, sir.
Yeah. Okay, and I will be wrong. My statement will be wrong with 5% of the time. Mostly it will be correct. With 5% time, I will be wrong. That is why this number is there.
And sir, this mu a we have seen that this part is fixed. That mu a minus 0.01 and
yeah.
So this is what we have assumed, that we'll get an answer mu a which is the right answer, which is the actual answer, and with
No, this is fixed, but you don't know what this is. Okay. What we are saying is we did not lie in this correct range. Okay. Our answer will not be within plus or minus 1%. That error will be 0.05. Okay, but the actual thing, what actual is mu A, you will know only after the election is over. Then only you will know mu A because you've asked everybody. Okay, until then you don't know what is plus or minus 1%. Okay.
Yeah, okay, sir. Thank you, sir.
Yeah, all right. So
So
that is what
the
this is.
confidence level, is it assumed or is it given?
So both your accuracy and the confidence level you have to choose.
Okay, sir.
Okay, so if this is something that is very important and you cannot be mistaken, then you may want to increase the confidence to 99%. Okay, if when will accuracy not be important? If there are only two candidates, okay, then plus or minus 5% is okay. But if there are 25 people, you better be, even accuracy should also be good. So like that, you have to decide based on the problem at hand. Does that answer your
Okay.
question? Yeah.
Yes, sir.
Okay.
Okay.
All right. So now what we will do is that we want to design this. I won't show you how to design this, but we know from the previous discussion over here, right? We know that if you want to bind it, you have to use this formula, variance of mmn by epsilon square. Okay. So let us do that. Okay, so my epsilon is equal to 0.01. Okay, if I want 0.05 error level, okay, that is given by variance of mn by epsilon square, right? That is what this is. I'm equating this. I want to choose my n in such a way that this is 0.05, right? So I use Chebyshev. Let me repeat. I understand that this can be confusing. We know that this, right, this whole thing, okay, is upper bounded by variance of mn by epsilon square, okay, which is actually this part is equal to sigma square by n epsilon square, right? That is what it was. All right. So I want I have chosen epsilon to be 0.05. I have chosen this quantity to be 0.05. This is the error probability. Error probability has to be less than 0.05. So that is what I'm going to do. Okay, so that is why I have equated this way. Okay, so let us solve for n. So 0.05 is equal to sigma square by n epsilon square. Okay, now epsilon I know, but unfortunately I don't know sigma. Okay, so what is sigma? Sigma is actually given by mu a into 1 minus mu a. This is the variance of Bernoulli, right? So we don't know this, but we know that this is sigma square. We know that this is upper bounded by what number? Anybody? What is the upper bound for Bernoulli random variable variance? So when mu a is equal to half, right? That is when it will be the largest. Half into 1 minus half, which is half. So this is 1 by 4. Okay, so even though we don't know this, we will upper bound it. So what I mean to say is, we will say this is less than or equal to, okay, 1 by 4n epsilon square. Okay, now we are ready to solve for n. So n has to be, yeah, so you have to be careful. So which is bigger? So sigma square, let us see. Anyway, if you choose larger than, just work out the algebra. I may not have put the signs correctly, but if n is larger than, what is this? 4 into 0.05 is 0.2, okay? And epsilon square is, something is wrong, right? What am I doing mistake?
Zero 0.2 is in the denominator.
0.2 is in the denominator. Yes, that is correct. So 0.2 in the denominator is 2 by 10, 5 in the numerator. Okay, 5 into, and epsilon square will be in the denominator, right?
5 into 100 square.
Yeah. So basically, if n is greater than 50,000, I can get this level. Okay.
So,
Is
but
this
I
clear?
think the inequality has gone wrong somewhere.
Inequality has actually gone wrong somewhere. So let us do one thing. Let us say this is approximately equal to. Let's not bother to put inequality.
So
Okay.
it should be 0.05 is greater than equal to 1 over 4, I think. 1 over 4 and epsilon square. Then
So
it will be
0,
correct.
yeah. 0, 0.5. Yeah. So this is the upper bound. Yeah. You have to put like this. I want an accuracy which is less than this. So this is the accuracy which I will get. Okay. So I will put it this way. Then it will be correct. Who asked that? Tanuja, was it you? Now is it clear to you?
Yes, sir. It's clear.
Okay, good. So this is what you will get. But if you see the exit polls that are conducted, if you really see in Times of India and all, when they say exit poll, they will typically do something like 3,520, 4,000 people. Okay, they never do 50,000. 50,000 we got because we used Chebyshev. Okay, Chebyshev performs badly. Okay, so that is why we will use something better now. Okay, so let me just ask before I move on to the next topic, let me ask people if so far is there any confusion, questions or anything till this point. So please let me know if things are okay. Mahendra Kumar, what is mu? Did I answer your question? I hope it was something earlier, but yeah. Karthik, is okay everything? All right. So this is so what we saw is a direct application on how we can design our polls. Okay, so that is pretty interesting. This is the first application that we saw of weak law of large numbers proof. So we can do something better, and that is the next topic which I'm getting into, which is called a central limit theorem. Okay. All right, so let's get into this topic. This is going to be, it's going to make our life much more easier. Okay, and things are going to get more nicer. All right, so coming back to the estimation problem, what we did was Mn is equal to x1 plus x2 all the way xn by n. Okay, so this was the estimation problem. This was our estimator. And we said expected value of Mn goes in probability, sorry, Mn goes in probability to expected value of Mn, which is equal to mu. And this we called as weak law of large numbers. We also saw an application where we used the Chebyshev, okay, to solve for this. What is that? To solve for n. That's what we saw. Now we saw that this number is very high. We can do better. Okay, so that is where we are going next. So what we are going to do is we are going to introduce some more notation. Okay, so Mn is equal to x1 plus x2 plus xn by n. Okay, we are going to call Sn is actually the sum of n things, x1 plus x2 plus xn. Okay, so this is Sn. So Mn basically is Sn by n. Okay, so let us now write what and all we know about expected value of Mn. Expected value of Mn we know is mu. Variance of Mn we know it is sigma square by sigma squared by n. So that is variance of Mn. So similarly, let us try to write what is the expected value of Sn. Okay, so that is easy. So you are just having all of these things added. Each of them is going to give mu. So this will be n mu. Okay, and variance of Sn will be so variance, since these are all IID, right? Remember, I was kept on saying it is IID. So every sample is independent. So when you look for the variance, it is sum of all the variances. Each variance is sigma squared. So this will be n sigma squared. Okay, so this much is enough to really start stating the central limit theorem. Okay, the first I will state it informally and then we will make it formal. So the informal central limit theorem, the useful central limit theorem. Okay, so informal is actually useful. So this is where I'm telling something different from what Sitsiklis teaches. Okay, so this is the useful one, central limit theorem. So what I'm going to say is that Sn, okay, Sn can be approximated as normal distribution with mean n mu and variance n sigma squared. This is one. You can also say Mn is also approximately normal with mean mu and variance sigma squared by n. Okay, these are informal statement, true for n greater than or equal to 20. Something like this, you can always approximate, provided n is large enough, you can do this approximation. Okay, so what is the meaning? How do we use it? So let us look at something what Sitsiklis has done and try to solve that for ourselves. Okay, so let's pick Sitsiklis notes and pick some things. Okay, so let us pick these three things. Control Shift. Okay, so yeah. Okay, so let us apply it to binomial. Okay, so that is the first application we will see. So now let us choose n equal to 36. Okay, let us choose probability of each thing being 0.5. Okay, now we are doing Sn. So what is Sn? Sn is the sum of 36 tosses. Okay, Sn is x1 plus x2 plus x3. Okay, plus all the way up till x36. Okay, so now my question is, how do we solve for p Sn less than or equal to 21? Okay, so this you can do directly by the binomial formula. Okay, so this is the binomial distribution formula. You sum over all the values of k less than or equal to 21. So that is one way to do. Okay, but we can do something better. Okay, so let's try to do that. So I said that Sn, okay, has the distribution normal. Okay, so mean is half. What is n mu? 36 into half. What is that? Yes.
18.
18. Okay, so 18 and variance. So sigma square. So sigma squared for this one is how much? 1 by 4, right?
Yes.
Yeah. So sigma squared is 1 by 4. So n times sigma squared by n, right? So that will be 1 over, yeah, so 36 times this. So this will be 36 by 4. I hope I have done this correctly. Okay. So now what we can do, yeah, so this is this. So probability that Sn is less than or equal to 21 is same as probability that Sn is less than 22, because Sn is taking discrete values. It doesn't take any value between 21 and 22. Okay. Now we can treat it as normal. Okay. And then we can ask for the normal distribution. So this one, I will call it as, let us say this whole distribution, that approximation that I am doing, I will call it as some other thing. Okay, so let us call this as xn. So this is an approximation. So this is same as probability that xn is less than 22. Is that okay? I'm approximating Sn as this xn. This whole thing I'm calling it as xn. Okay. So what I will do now is go ahead and actually compute this. But to compute that, I need to first convert it into standard normal, right? Otherwise, we can't do it. So to convert something to standard normal, what do? We multiply, we subtract from the mean and divide it by the variance. So that's what we will do next. So this will be same as probability that this will be actually equal to probability that the standard normal Z, okay, is less than 22 minus mean, which is 18, divided by 36 by 4. 36 by 4 is actually 9, isn't it?
Sir, we take the
Square
standard
root.
deviation there, right?
Yeah. Thank you so much. So this will be 3. Okay, so this will be actually equal to probability that Z is less than 1. Okay. Now to answer this, you remember, right? So what is the meaning of Z less than 1? Now Z is a standard normal. Okay, so what we have is 0. Okay, and what I'm asking, this is -1, this is +1. Okay, I'm asking for this entire range. What is the probability that this is happening? Okay, I know that in standard normal, the mean is 0 and the variance is 1. Okay, and the standard deviation is also 1. So I know that Z lying between 1 and -1. What is this probability? Yes, someone? What is this probability?
So, Z
0.68.
is less than 4 by 3.
Sorry?
Z is less than 4 by 3. You return the 1. Probability that Z is less than 22 minus 18 by 3 is equal to 4 by 3.
It is 4 by 3, right? It's not 1 by 3, correct? Yeah, okay, no problem. So this is 4 by 3. So I cannot directly use this, okay? So I have to look up at standard normal table. So that we can do. 4 by 3 is, what is this? So let's not go into this directly yet. So this is probability that Z is less than 1, 1, 3, 3, 3, 3, right? So let me open standard normal table and try to solve this. Okay, so 1, 3, 3, 3, 3. So if you see 1, 3, 3, okay, it's happening with the probability this. So am I looking it correctly? Yes, I think so. So 0.4082. Okay, something is wrong. Can someone tell me what I have done mistake? Mm, 20
Sir,
mean
why
is
did
8.
we take it SN less than 22?
Yeah. I mean, I took it as 22 because 21 and 22 we can take because we will next do it with 21.5. But because SN is taking at discrete points, right? 20, 21, 22, there is nothing between 21 and 22. So that's why we took 22.
Sir, but then instead of that, we can just calculate P of xn less than equal to 21.
Less than or equal to 21. That we could have done. As a compromise, we will actually do 21.5 later. Okay, as a compromise, we will do this. But before that, there is a mistake. Somewhere I have done a mistake. Someone has to point out to me now. What is happening? N sigma squared, is that correct? Half into half, 1 by 4, n sigma squared, 4 by 9. Yeah, that is correct. This is 3. 22 minus 18, 4 by 3, 4 by 3. Yeah, it seems to be correct. 1, 3, 3, 3.
Sir, we got our mu equal to 18, right?
I think
Then
this,
SN is a normal
this
distribution of n times mu.
and SN is a normal distribution of. No, this is
N times.
standard. No, this standard distribution, this standard normal table, I'm not looking properly. Okay, that is the problem. So let me just go to the proper standard normal table. Yeah, let us look at this. Okay, so just hold on, just hold on to that thought. So 1, 3, 3.
Sir, you are
Sir,
muted.
it seems mute.
Sir, you are muted.
Sir, you are on mute.
Okay, so what I said is sorry about that. So I got disconnected from Wi-Fi for whatever reason. But does anyone know what mistake I have done so far? If not, okay, someone pings. Sir, see standard normal. Okay, let us see. What's that? Standard normal cumulative distribution table. Isn't that what I'm looking here?
We can't see your screen, sir.
Oh, okay. Let me share again. Sorry about this. Okay. All right. So this one is what I saw. I will have to check again, but I think this is the standard normal distribution table itself. All right. So yeah.
Sir,
So
I
once
think
more-
the table we were looking back before this was not standard. It had mean as 0.1 and standard deviation as 0.01. That was one problem.
So this mean is standard normal, right? This one. What is the mean here? 22 minus 18. I have subtracted away the mean.
I'm talking about the table, sir.
Oh, the table. Okay. Okay, here.
This seems to
What?
this, yeah. The table that we looked before this had mean 0.1 and standard deviation 0.01, which are not the standard means we.
Yeah. But here, if you look at this table, the error that I'm getting is 0.9082. Okay, in this table here. So let me do one thing. Let's not dwell on this much. It's just a matter of checking the algebra.
Can it be because of maybe?
Because of? Can it be because of what?
Sir, we have considered 22.
Yeah.
If
If we
you look
take
at less than
21.5, it
21.
is 0.87 something.
Okay. So anyway, so since we took it as 21, okay, if you look at 21, you get better, you're saying. So if you look at 21, then at 1, yeah, so we get 0.84. Yeah, correct. So if you look at 21, okay, let me do one thing. Let me not rush through this topic. It's an important topic. So what I will do is I will explain the rest of the thing in a one more video and I will share it with you. Okay, so let me not rush through it. So let us just quickly recap what we have discussed and let's not get lost and feel dejected because we got one wrong thing. Okay, so what we have been looking at is basically some statistics. And the primary thing that we saw is like different modes of convergence. Okay, we first only talked about convergence in probability. Convergence in distribution is what we were heading towards, which is the central limit theorem. Okay, and then we saw some examples and everything. And what we said, I think the informal statement of central limit theorem is what is useful. Okay, so we said that Sn converges to n mu and variance n sigma squared for n greater than 20. And we were trying to look at an application and something has happened here. Let me just, what I will do is I will explain this in the next class. Okay, so this is an important topic, so I don't want to rush it. So what I will do in the next class, because I heard from all of you that there are some 2 quizzes that are scheduled in this week. So this week I will not do any offline recording. Next week onwards, we will do that. So what you will have is you'll have 2 classes, Monday and Tuesday, and there will be an offline video for you to watch. But this week, we will not do that. So this week, we will stop here and we will pick up from the same point in the next class from here. And I will resolve all these questions and we'll move on from there. Okay. So let me just stop here. And yeah, so if there are any questions you can ask, I will be here.